In this video, I'll talk about molecular solids. Molecular solids consist of molecules that are held together by dispersion or dipole-dipole interaction. The first example is ice. In ice, water molecules are held together in position via hydrogen bonding. Hydrogen bonding is the strongest type of attraction in the dipole-dipole interaction category. So still it's dipole-dipole interaction, but in particular, the dipole-dipole interaction between water molecules is called hydrogen bonding. The melting point of ice is 0 degrees Celsius under 1 atm pressure. Now let's look at two other examples, dry ice and solid O2. Dry ice is CO2, carbon dioxide, in the solid phase. What's in common between these two? Neither CO2 nor O2 has a non-zero dipole moment. So their dipole moment is exactly 0. That means there's no dipole-dipole interaction between O2 and O2 or between CO2 and CO2. So what's holding two CO2 molecules together? What's holding a huge number of CO2 molecules together to form a CO2 solid or dry ice? It's dispersion. The melting point of dry ice is negative 57 degrees Celsius under 5 atm pressure. The melting point of O2 is negative 220 degrees Celsius. Why so low? Compare their melting points with water. The reason is simple. For these two molecules, again, there's no dipole-dipole interaction. The molecules are attracted by dispersion, and these two molecules are fairly small. The dispersion is fairly small. Therefore, it's fairly easy to melt dry ice and solid O2 under a very low temperature. Why did I specify the pressure here? This is because under 1 atm pressure, dry ice sublimes. It undergoes sublimation under 1 atm pressure when the temperature is high enough. The liquid phase of CO2 exists under 5 atm pressure or even higher. Again, under 5 atm pressure, if the temperature is negative 60 degrees, you have solid CO2 or dry ice. At negative 50 degrees Celsius, you get a liquid. Liquid CO2, again, you have to have a fairly high pressure here. But the main point here is, for these two molecules, there's no dipole-dipole interaction, there is dispersion. However, because the molecular size of these two molecules are fairly small, the dispersion is also fairly small. Therefore, it's very easy to melt these two solids. Finally, I want to talk about long-chain fatty acids. There's a lot of dispersion between two long-chain fatty acids. Long-chain means they both have a long carbon chain between the interacting molecules. When that's the case, we can roughly estimate that the dispersion attraction is proportional to the size. And also, if we're talking about fatty acids, there are OH functional groups. In particular, it's actually so-called COOH functional group. And there are dipole-dipole interaction between those functional groups. And therefore, long-chain fatty acids tend to have high melting point. For example, if you have a carbon-20 chain, the melting point is 75 degrees Celsius. So this is a solid at the room temperature. You have to heat it up to above 75 degrees Celsius, again under 1 atm pressure, to have liquid fatty acids. So you may wonder what's the structure of the long chain fatty acid solid. It's right here. So you have 6 such long chain fatty acids on top, and then this on bottom. And over here you see the dipole-dipole interaction. And actually this is also hydrogen bonding, because you have, this is a little bit too small, but I want to make it bigger so that you can see clearly. You have positive charged hydrogen here interacting with the negatively charged oxygen. And also over here you have partially positively charged hydrogen atom interacting with partially negatively charged oxygen. So there's hydrogen bonding here. It's very important. It's significant. But also it's significant to realize the dispersion between 2 neighboring fatty acids. For example, between this one and this one. Because of the large molecular size, again, because the dispersion force is roughly proportional to the molecular size. Look at this and this. There's a significant dispersion. It's a type of attraction that hold those fatty acids together. Therefore, this long chain fatty acid has a fairly high melting point. And you can imagine if we have a shorter carbon chain, let's say only 2 carbons, that's called acetic acid. And acetic acid has a much lower melting point than this carbon 20 carboxylic acid, because of the smaller amount of dispersion. All right. Okay. This is water. This is 1 unit cell of water. So you can see water molecules form a hydrogen bond. Over here, this the green stick is a hydrogen bond between 2 neighboring water molecules, and between these 2 there's another hydrogen bond. And over here this is CO2. Again, this is CO2. This is, I think, face-centered. So you have 1, 2, 3, 4, 5, 6. The one behind this is hardly seen here, but there's one on the front, one on the back. So this is face-centered cubic unit cell. Anyway, between 2 neighboring CO2 molecules, there's only dispersion, and the dispersion force between 2 CO2 is much smaller than the dipole-dipole interaction between 2 water molecules. And over here, this is very long chain fatty acids. Now I'm going to ask you to solve this problem. Let's rank the melting point of the following molecular solids: ammonia, nitrogen, and this contains 8 carbon atoms, right? And this is OH functional group. So this is octenol. Okay, it's similar to alcohol, but it has just more carbon atoms. And this is a linear carbon chain to ensure the maximum contact between 2 neighboring octenol molecules. All right, so let's look at this nitrogen first. There's a 0 dipole moment in nitrogen. Therefore, between 2 neighboring nitrogen molecules, it's going to be just dispersion only. And the dispersion is small because the size of N2 is small. The contact area between 2 neighboring nitrogen molecules is small. Therefore, I expect nitrogen has the lowest melting point. Let's look at ammonia. There's hydrogen bonding between 2 neighboring ammonia molecules, and that's pretty strong. So I think the melting point of ammonia is higher, or much higher, than the melting point of nitrogen. Now finally, this one. This is octenol, or in organic chemistry it's 1 octenol. And then you can see between 2 octenol molecules there's going to be hydrogen bonding because of this OH. Both this H and this oxygen can participate in the formation of hydrogen bonding, And also take a look at this carbon chain, really long chain, and also it's linear that ensures the maximum contact area between two neighboring octenol carbon chains. Therefore, there's dipole-dipole interaction, there's dispersion, and the dispersion is fairly strong. So I expect this one octenol has the highest melting point. Let's look at the answers. Well, indeed, this one octenol has a negative 16 degree Celsius melting point, higher than ammonia. This is the melting point of ammonia, and nitrogen has the lowest melting point, negative 196 degrees Celsius. But now you may wonder, by looking at this, hey, it has such a great dispersion, why its melting point, negative 16 degrees Celsius, is lower than water? Well, there's a reason. In water, you can form two hydrogen bonds per molecule. All right. So you may wonder, wait. If you look at this molecule, there are 1, 2, 3, 4. There are 4 hydrogen bonds. Why did I say 2? Well, only because this hydrogen bond is formed by two water molecules. All right. So it's shared by two water molecules. So when I counted the number of hydrogen bonds, I counted half of this for this center water molecule and the other half for this one. So half, 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 a total of 4 hydrogen bonds. So if you look at water molecules, each water molecule can form on average 2 hydrogen bonds. Over here, there's only 1 hydrogen bond. So roughly speaking, we want to say, yes, there's a lot of dispersion between two adjacent long carbon chains, but maybe this dispersion is slightly weaker than a hydrogen bond. That's why this molecule has a lower melting point than water. How can we have a fatty acid with a higher melting point than water? Very simple. You just increase this carbon chain from carbon 8 to carbon 20, or maybe carbon 30. And then I'm pretty sure that this carbon 30 alcohol has a melting point higher than 0 degrees Celsius.